Welcome back, everyone, to our second module on the Hick-Hyman Law. Now, in this module, we're going to be delving into how response selection works. And we're going to spend a bit of time on response selection in this module and in the next module. So response selection, remember when we talked about it in the first module, we said it's kind of simple in a way. You're deciding which response to make. So based on all the input to your system and knowledge of your body in space and what's happening, you need to select a response. And we're going to look at how that occurs when you're faced with different number of stimulus response alternatives or different numbers of choices. So here's our basic model of information processing. And with Donder's subtraction method, we had to break this down into 5 stages and substages. Today's content is a little easier, and we can stick with just the main 3-stage model. And we're going to be focusing on how response selection changes. So here's an example. So if you imagine a batter facing a pitcher, the pitcher throws many different pitches. And you might ask yourself why, and that's not a very difficult question. You know, they're trying to elude the batter. They want to strike out the batter. They want to make it difficult for the batter to hit the ball. I mean, imagine in Major League Baseball, if they got rid of the pitcher and put in a pitching machine that threw the same pitch every time, it would be basically a home run contest. So the pitcher throws many different pitches to elude the batter. In this kind of simplified example, they're showing maybe 6 different pitches. I have a list here of types of pitches. So these could be a changeup, curveball, cutter, forkball, fastball, knuckleball, screwball, sinker, slider, or splitter. And then there's even more possibilities than that, because even just a fastball, you could throw it a little bit faster or a little bit slower. You could throw it in the top right corner or the bottom left corner. So there's many possibilities for the type of pitch and location and speed that the pitcher might throw. And today we're going to look at a law that shows us how reaction time changes with the number of different alternatives. So think the number of different pitches. So before, we will come back to batting and the pitcher later, but let's look at the very fundamental research in this area. And this was done by Merkel back in 1885. So not too long after kind of Donder's time. So he was looking at reaction time, and as with that era, instead of a keyboard button, which they didn't have back then, but they did have telegraph keys, for sending Morse code. So he arranged 10 telegraph keys so that your 10 digits would fit on top of these fairly comfortably. And what would happen is, in front of the participant, they would get a stimulus, and the stimulus would be 1 to 5 in Arabic numerals or 1 to 5 in Roman numerals. So maybe the stimulus on this trial, it would be random. Let's say it was a 5, so the participant would learn that with a 5, what they need to do is press their left pinky as quickly as possible on that key. So if you see a 5, press the left pinky. 4 would be, let's see, the left ring finger, and so on and so forth. And the participants in this experiment were given lots of trials so that they would become comfortable with this mapping between the stimulus, 1 to 5 Roman or Arabic numerals, and the response, pressing one of the 10 keys. Now what Merkel did is he altered the number of stimulus and response alternatives. So what we just talked about, we could call 10 choice. So there were 10 different stimuli that required 10 different responses. And then what he did is he made this task easier and easier. So in 9 choice, he got rid of 1 stimuli, so there was no 5. And he told the participants this. He would say, okay, in this block, it's just going to be these 9 fingers that you're using. So 9 stimuli and 9 responses. And you can imagine this is going to be easier and easier and easier until we get to 2 choice, which we already saw with Donder's. And in this case, I think it was just the 2 thumbs that would be responding. All right, let's give this a try. Let's try 2 choice, which is, I think we would predict would be the easiest. And then we'll try 10 choice, which is the most difficult. And as you try 2 choice, try to feel how long your reaction time is, and then let's compare that to 10 choice. Okay, so 2 choice. So if you see Arabic numeral 1, left thumb, and if it's the Roman numeral 1, right thumb. Here we go. Okay, so pretty straightforward. Is there another one? Oh, there's one more. Okay, there we go. I think we did 5 trials there. Okay, let's try 10 choice. Now this is going to be a little harder than it was in the actual experiment because participants got to do a few hundred trials first to learn this mapping. But let's try 10 choice and see if you can feel what happens to your reaction time. Here we go. Okay, so what you probably felt or hopefully felt was that reaction time was much longer with 10 choices than with 2 choices. And that's, a fairly straightforward finding, probably not too surprising. And here we can see a plot by Merkel. This is a very old paper, so this would be a hand-drawn graph, and I've kind of redid the labels so that we can read them clearly. So here's the reaction time. Here's the number of stimulus response alternatives. So this is 2 choice, this is 10 choice. And what we can see is that as the number of stimulus response alternatives increase, so too does reaction time. There's a couple of more interesting things here than just that basic pattern. First of all, what Merkel noticed is that early on, so let's say 3 choice to 4 choice, there was this very large increase in reaction time. And 3 to 4, we've increased by 1 stimulus response alternative. But let's compare this to 9 to 10. That's also an increase in 1 stimulus response alternative, and yet we see a very small increase in reaction time. And what Merkel is basically noting is that this isn't a linear pattern. We'll see it's logarithmic. There's large increases early on, and these increases get smaller and smaller. So that's the first important finding. The second important finding is, well, why does reaction time increase? And Merkel argued that what's happening, what's different between, say, 2 choice and 10 choice, is the duration of response selection. So in 2 choice, yes, you have to identify the stimulus. You then have to select a response. Okay, is it left thumb or right thumb? Once you select the response, you can program that response. If we compare this to 10 choice, so a much harder task, what he said is that, stimulus identification and response programming probably about the same duration as 2 choice. So, identifying a number doesn't matter whether it's 1 to 5, it's about the same. Programming the thumb, index finger, middle finger, that's about the same. The reason reaction time changes in 10 choice, so why is it much longer? It's because response selection takes longer. And this is neat because within this paradigm of altering the number of choices or stimulus response alternatives, reaction time will change, but we can infer that's because of a change to just response selection. If we depict that on the previous figure, so here's 2 choice and response selection is short, so overall reaction time is also short. If we look at 6 choice, reaction time is longer. Why? It's because just response selection got longer, just the green box. 10 choice, even longer reaction time. And again, the hypothesis is that it's just because of an increase in response selection. So it's kind of nice because in this experiment, we know that changes in reaction time are because of changes to response selection. So we've isolated a single stage without having to do any of the subtraction done by Donders. All right, next up in this kind of history of this research come Hick and Hyman. And they were both very famous cognitive psychologists. In fact, they were some of the earliest cognitive psychologists. In this photograph, we can see Hick is here in the background. And this is a photo of Hyman on this side. And this photograph has a lot of the originators of cognitive psychology. The picture I found already had 3 circled, but the most famous is probably this one in green here. This is Alan Turing. And I have a couple of stats about him. Now you may have heard of him before because he was very crucial during World War II. He cracked the Nazi Enigma code. Let's find my stats here. Here we go. So he cracked the Nazi Enigma code, which was a huge accomplishment, and it was predicted that it shortened the war in Europe by 2 years and saved over 14 million lives. So that's, an incredible impact. So we can see Hick in the background here. Here's another picture of Hick. And this is him in the laboratory. And I think he's actually working on the device that he used to test the number of stimulus response alternatives. So here are the telegraph keys, and here are the lights. So he's got a lot of them, and it looks like on this block he's maybe setting up maybe 5 stimuli. And then so he would need 5 response keys down here. So Hick and Hyman were interested in Merkel's relationship, and this is almost 100 years later. They wanted to reinvestigate this relationship. So the first thing they did is they wanted to replicate Merkel's experiment. So, do we still find the same thing? Or maybe Merkel had really old equipment, and maybe we don't see the same pattern. But what they did here, and here you can see Merkel's original data in the squares. Here's Hick's data, actually. He ran 3 different experiments, and he found basically the same relationship. Reaction time was a little quicker overall. That could be the participants tested. Maybe his equipment was a little better at measuring reaction time. But the important thing is that this relationship was the same. We see a logarithmic or a nonlinear increase in reaction time with the number of stimulus response alternatives. The important thing that Hick and Hyman added is they looked at this curve and they said, hey, you know what? I think this is a logarithmic function. And here we can see a logarithmic function. So see this curvature? Looks very similar to this curvature. And we're going to spend quite a bit of time on this. If you're not familiar with logs, or if it's been a while since you've used them, that's okay. We'll go through them. And they're really just another way to write an exponent. And I don't think our exponents are as scary as logarithms. So here's Merkel's original data. And the hypothesis here is that this is logarithmic. Now, if it is logarithmic, the way to test it is we want to convert the x-axis. We're going to go from n, the number of stimulus response alternatives. We're going to add in log to the base 2. And if we do this and replot the data, if it then looks like a straight line, then originally we did have a logarithmic function. And you can see here that yes, this data, we add the log term, we transform the data, and it does look like a pretty good straight line. It's not perfect. This is a perfect straight line here, and it curves away from it below and then above here. But this is surprisingly linear for any sort of human experiment. A little more on that. So first, if we then want to find what's called Hick-Hyman Law, what we do is we find the equation of this line. And if we go back to our high school math, remember the equation of any line is y equals mx plus b. And then what we need to do is solve y, mx, and b for this line, and we would have Hick law for Merkel's data, for example. So that's Hick-Hyman law. We're going to talk a lot more about this. But why is this interesting? Well, if we think about scientific laws, they're very powerful. A few examples, if I can remember them. We have the universal law of gravity. Something about gravity. Should I check my notes here? Universal law of gravity. What do we call this one? Newton's universal law of gravitation. I was close. We have Einstein's theory of relativity, E equals mc squared. When I added this, I'd always heard of this, but I don't think I knew what it meant. And what this equation is saying is that the amount of energy in a mass is equal to the speed of light squared times the mass. And if you think of speed of light, huge number, we square that even bigger, we multiply that by a mass, even a small mass, and that gives us a tremendous amount of energy. And this is where the idea of kind of nuclear fusion and nuclear explosions come from. That there's a huge amount of energy stored in chemical bonds that if we can release, we can produce a tremendous amount of energy. We have the ideal gas law. What is this one called? Ohm's law. I was like, V equals IR. Ohm's law. Related to voltage, induction, and resistance, or current and resistance. And if you've taken biomechanics or physics, you may recognize the kinematic equations. So there are lots of laws out there. Some of these you've probably seen before. But what you might realize is that these laws are all about the physical universe. There are very few laws that tell us about how the mind processes information. So whenever we find one of these, it's very exciting. So this is our first in the course, Hick-Hyman Law. We'll see a couple of others, but they're very few and far between. The brain is typically not so simple that it can be described with a simple logarithmic or linear equation. So there aren't very many scientific laws of the mind. So that's why it was very exciting that Hick and Hyman said, yes, there's this pattern here. The pattern's not that surprising that reaction time increases with the number of choices. The surprising thing is that it can be modeled quite accurately with a logarithmic relationship. All right, let's talk about logs because we're going to need to understand these. So here we have log base 2 of 8. We want to solve that equation. And if you already know the answer to that, great. If you don't, though, we can simplify that logarithm by rewriting it as an exponent. And you can think of logs as just mixed up exponents. They're written in a different way. So if we want to rewrite this, well, actually, take a step back. Let's think of another question. Exponents, easier, right? So if I asked you, what is 2 to the power of 3, that's probably easier to solve. And if you're a little rusty on exponents, that's okay. So 2 to the power of 3 is 2 times itself, 3 times. So we've got 3 2's, 2 times 2 times 2. So 2 times 2 is 4, 4 times 2 is 8. In other words, 2 to the power of 3 equals 8. Now this logarithm is really just that exponent kind of rewritten. So how do we go from here to here? So 2 to the power of what equals 8? Well, we know 2 to the power of 3 equals 8. And that question is really the same as log base 2 of 8 equals what? So how do we go from here to here? So what we do, we're always going to be using log base 2. So it's going to be 2. What we're trying to solve is how many times is the exponent in this equation. So that comes down there. And the 8 in brackets, that's the solution when we rewrite it as an exponent. So when you look at a log, you can rewrite it as an exponent to make it easier to solve. Okay, so we know 2 to the power of what equals 8? Well, 2 to the power of 3 equals 8. And if we want to put that back into log form, we would write it as log base 2 of 8 equals 3. So we're going to need to know our powers of 2. These aren't too hard, thankfully. So 2 to the power of 1, so just think of 2 is 2. 2 to the power of 2 is 2 times 2, which is 4. 2 to the power of 3, we just saw that. 2 times 2 times 2 is 8. And the highest we'll need to go here is 2 to the power of 4, which is 16. There's one other kind of odd one, and this one you might just need to memorize, and that 2 to the power of 0 equals 1. So anything to the power of 0 equals 1. It's a little odd, but that's how powers work. Okay, let's take a look back at Merkel's data and see if we can understand how this data has been transformed. So here's the original data, and we have reaction time on the y-axis, n, or the number of stimulus response alternatives, on the x-axis. Over here, it's still reaction time on the y-axis, but we've transformed the x-axis so that it's now log base 2 of n. So let's look at how that's done. And some of these logs are easier to solve than others. 3, 5, 6, 7, 9, and 10, they're going to take a calculator because they have a decimal point. So we're going to stick with the easier ones, 1, 2, 4, and 8. So let's look at our first point here. So this point here, on this graph, the x value is 1. The y value, we'll guess it's about 180. So that's how we describe that point on this graph. If we want to take it to this graph, we're going to have to convert the n value from 1 to log base 2 of 1. So log base 2 of 1, what does that equal? Well, let's rewrite it as an exponent. Oh, I seem to have skipped that here. Can I do that? I can do that here. Okay, let's rewrite that as an exponent. So it's going to be 2. Oh, my writing's not the best with the mouse. To the power of what? Oh, no. Okay, pretend that's an equal sign. Equals 0. Oh, my. Why did I try doing this? Okay, so 2 to the power of what equals 0. And remember, that's kind of the weird one where, it's 2. Oh, my Lord. 2 to the power of 1. I think I need a tablet here, don't I? Equals 0. Oh, boy. So in other words, log base 2 of 1 equals 0. So that is our new x-coordinate. On this graph, it was 1. But here, we're solving log base 2 of that, which is equal to 0. The reaction time stays the same. So the y values are the same on both graphs. So the first point was 180 over here. And on this graph, it's going to be 0, 180, which is this point here. And we can do that for all the points. We won't do all the points, but we can at least do the ones that have easy logs to solve, like 2, 4, and 8. So here's 2. And on this graph, we can just read off the values. It's 2. We'll guess it's about 310. Over here, to find that point, we're going to have to solve 2. Oh, am I going to do better this time? I don't know why I'm trying this again. This is a little better. 2 to the power of what equals 2? Well, we know it's going to be 2 to the power of 1 equals 2. Oh, don't know why it does that. Okay, so we're solving this log, and we know the answer is 1, because remember it took, the exponent here was 1, so it's going to be 1. So this point goes from being 2, 310 to 1, 310. So the second point goes from here to here. And we can do that for the points that have easy logarithms to solve. So this point is 4, 425, and on this graph, it's going to be 2, 425. So notice the y values are staying the same because on both graphs, it's just reaction time. But the x values change because we go from n to log base 2 of n. Okay. And one final example, the last logarithm that's easy to solve. This point goes from 8, 610 over here to 3, 610. So a note about logarithms. So logarithms can have any base, and if you look at your calculator, it's probably log base 10. That's the most common base. But here, in this experiment, it was log base 2. Now, why was that important? Well, the same time Hick-Hyman's research came out, there was a very important research being developed called information theory, which is different than information processing. And information theory was all based around log base 2. Now, what is information theory? Well, let me give you a few points, but then I'll give you a demonstration that hopefully makes more sense. So information theory says that the amount of information in a signal is measured in bits. And if you're thinking bits, signals, binary, you're on the right track. This was all about transmission of information, so kind of early theory around how the internet, cellular signals, things like that would work. Now, what is a bit? So 1 bit is the amount of information needed to reduce the uncertainty of the signal in half. I'll demonstrate this. Also, I'm not going to test you on information theory. Okay, so I can demonstrate information theory with the game of Guess Who. And let's simplify the game. Let's say you're trying to guess from 16 faces here. Can I go back to normal cursor? How do I turn this off? Oh boy. Laser pointer? Okay, laser pointer's fun. All right, let's say you're trying to guess who the person is from 16 faces. Now, the ideal strategy is to ask questions that eliminate half of the alternatives, half the choices, half the stimulus response alternatives at a time. So maybe the first question, let's say half the people have brown hair and half people have black hair. So you could ask, do they have black hair? And regardless of the answer, you could eliminate half the stimulus response alternatives. So there's 16 alternatives. We've asked one question. We don't know the answer yet. We're going to have to ask another question. Maybe half are male, half are female. We could ask that question. Regardless of the answer, we eliminate another half, just 4 this time. So 2 questions asked, we still don't know who it is. A third question, eliminate half the remaining alternatives. We ask one more question, and we now know who it is. So let's think about these numbers. We started with 16. We had to ask 4 questions, and that should be a little bit familiar from log base 2, because log base 2 of 16 equals 4. So information theory is built around log base 2, or kind of a binary system. And this was all about how information is transmitted. Think internet, cell phones, wireless, Bluetooth, anything like that. And it was exciting that they said, hey, with Hick-Hyman Law, we've now seen that maybe the mind transmits information similar to how we're creating devices to transmit information. So that's why it was kind of interesting and exciting that Hick-Hyman was based on log base 2, because it connected to information theory. All right, now let's look at an example of Hick-Hyman Law. So let's say we have a set of data. Oh, that 0 is way off, so it should be right over here. This is Merkel's original data, and let's say we want to find Hick-Hyman Law for these data. Well, we need to solve the equation of this line, of y equals mx plus b. So we're going to have to solve y, mx, and b, and let's look at that. So y, we're not going to put a number in here because we don't want to solve an individual point on the line. We want to solve the entire line. So for y, what we're going to put in is the label on our y-axis, which is reaction time or choice reaction time, or often just abbreviated as RT. M, that is going to be the slope of our line. X, this is the y-intercept. So we're going to have to look for when this line hits or intercepts the y-axis. And B, oh, sorry, I got confused there. X, this is the label of our x-axis. B, that is our y-intercept. And let me get that right on the next slide. Okay, so we want to solve the Hick-Hyman Law for these data. So y, remember, is just reaction time. We'll plug that in. X is log base 2 to the n. It's just the label of our x-axis. So we're going to plug that in. And there we go. We haven't even had to really look at the data yet, and we can already solve x and y. And they're always going to be the same for Hick-Hyman Law. For the slope and the y-intercept, we need to look at the actual data. So let's see, which one do we solve first here? I think we go the y-intercept. It's a little easier of the two. So we're going to follow this line here and see when it intercepts the y-axis. And we're going to have to estimate this point. And I think earlier I guessed it was about 180. So we'll plug that value in there. The last thing we need to solve is the slope of this line. So remember, m is the slope, or simply the rise over the run of this line. We can solve that with the equation for the slope, which is y2 minus y1 over x2 minus x1. So we're going to need 2 points. We need a first point, which that will be our x1, y1, and then a second point on this line, that's going to be our x2, y2. And here we could choose any points on the line, but the math is easiest if you pick points that are just one apart on the x-axis. So you could pick these 2 points, or this point at 1, and then go 1 over and pick this point at 2. But for this example, we'll just look at these 2 points. So this first point, we need to know the x and the y value, and the x value is 0, and the y value we've estimated is 180. So that's our x1 and our y1. And then this point, as we go up the line, the first point we come to, that's our 1 point, and then as we go up, the next point we're using is our 2 point, our x2, y2. And here the x value is 1, and the y value, we'll say about 310. So we now have our 4 variables. We can plug them into our slope equation. And notice that the denominator is 1. This happens when we pick points that are 1 apart, so it makes the math even easier. So our slope is 130. We're going to put that into the equation that we had already solve 3 of 4 of the variables, and that is our final answer. That is the Hick-Hyman equation for these data. Now, one thing that's important about the Hick-Hyman law is that they didn't argue that you're always going to see this exact equation with, the same slope and y-intercept values. Those values can change. Now, imagine you tested 20-year-olds on this kind of Hick-Hyman task, so 10 choice, 9 choice, all the way down to 2 choice, and then you tested older adults, maybe 80-year-olds. Well, 80-year-olds are going to have slower reaction times, and that's okay. And what you would see is if this is your young adults on the graph, the older adults, they would be slower, so their values would be higher, and maybe they would be even worse as you increase the stimulus response alternatives. So they would have a different y-intercept and a different slope. And that's okay. Hick and Hyman said that when you transform the data with log base 2, you will see a linear relationship, but the exact relationship can change depending on the exact experiment, the participants, the actual details of the task. So I think now is a great time for you to look at the practice questions, because there's an example of plotting data and then calculating the Hick-Hyman law. So it's kind of just like what we just did through the slides, but try it on your own now so you can see whether you're following the material. There's the practice questions without the answers, and then if you want to check your answers, there's a file with answers, and there's also a few comments in there that show kind of how I solved the Hick-Hyman law. All right, let's delve a little deeper into the Hick-Hyman law. So what does the intercept tell us? So from the original data, here we know the intercept was 180, and the intercept is when log base 2 of n equals 0. So what does that mean? Well, let's rewrite that as an exponent. So that's going to be 2 to the power of 0 equals n. And 2 to the power of 0, remember that's the weird one, that equals 1. So here, the intercept is when n equals 1, or there's one stimulus response alternative. So that's simple reaction time, right? If we think back to Donder's subtraction method. So what the intercept is estimating is your reaction time on the easiest possible reaction time task, simple reaction time. So the intercept, or B, is the duration of movement preparation when there is no decision about which response to make. Remember, simple reaction time, it's always the same stimulus. So Merkel didn't test simple reaction time, but if we think back to Donder's, remember it's stimulus, response, stimulus, response. There's no choice, just whenever there's a stimulus, make a response. And this is the easiest possible reaction time task. Because you know the response in advance, you can select that response before the go signal, program that response, and then when you get the go signal, all you have to do is detect, yes, I saw a light, and go ahead and initiate that response that was pre-programmed. So the intercept is telling us, or estimating reaction time for the simplest task, simple reaction time, when all you need to do during the reaction time is detect the go signal and initiate a response. What does the slope tell us? Well, remember we calculated for these data the slope was 130. Now the slope is how much reaction time increases when the number of stimulus response alternatives is doubled. And that's kind of key to the whole log base 2, but let me show that to you in this graph here. So here, log base 2 is 0, and we just calculated that that means there is one stimulus response alternative. When log base 2 is 1, there are 2 stimulus response alternatives, and then here there's 4, and here there's 8. So notice on this graph, every time we go up 1 bit, we're doubling the number of stimulus response alternatives. So 1 times 2, 2. 2, let's double this. 2 times 2 is 4. 4, double it. 4 times 2 is 8. And what the slope is saying is that every time we double the number of stimulus response alternatives, So here from 1 to 2, we should expect the same increase in reaction time. And in this case, it was about 130 milliseconds. So we go from 1 choice to 2 choice, reaction time goes up by 130. Now to go up another 130, we can't just go from 2 to 3, we have to double the alternatives. We have to go from 2 to 4. And you can see we have about the same increase in the slope here. From 1 to 2 goes up 130, from 2 to 4, 130. And then again, if we want to see another increase of 130, we have to double the stimulus response alternatives, this time from 4 to 8. So interesting aside here, measuring intelligence has been something that psychologists and other areas have been interested in for a long time. And it's difficult and it's controversial. And at one point there was a suggestion that, hey, maybe there's a relationship between the Hick-Hyman law and intelligence, specifically your slope value, which they called the speed of information processing, and your intelligence. And if we go back to this graph for a second, let's say this was one participant, and if we had another participant, and let's say they had the same y-intercept, but they had a shallower slope, this participant arguably would be better at the task. Because as we double the number of stimulus response alternatives, they see a smaller increase in reaction time. You know, if we had to pick which person to send to the Hick-Hyman Olympics, you know, we would pick this participant because they're better at the task. So they would have a smaller slope or m value than this participant. And there was a suggestion that maybe this participant is more intelligent than that participant. Now there was an early study on this relationship. It was in 1964 by Roth, and they did show a correlation between the intelligence, so they had to have an IQ test, which is, you know, kind of controversial, hard to measure, and they related that to the slope values on people's Hick-Hyman experiments, and they did find a small relationship between intelligence, so the more intelligent you were, the better you were at the Hick-Hyman task, or the lower your slope, the m value. Now, this study had, I think, fewer than 10 participants, so hard to really conclude that this is the case for everyone. But that's an early suggestion that maybe there's a relationship here. Now, many years later, this study came out, and I feel like it was kind of poking fun at this idea that there might be a relationship between Hick-Hyman law and intelligence. It's a serious paper though, and it's in a serious journal. And what they did is they said, okay, well, let's get away from this, testing intelligence of humans, because that's controversial. Let's go with the assumption that humans are smarter than pigeons. I think we can all probably accept that. So now what they did is they had humans do the Hick-Hyman task, and they looked at the human slope value. And okay, so here's humans, people. There's the slope value. And then they had two different breeds of pigeons. I don't know if one breed is smarter than the other, but they had them do the Hick-Hyman task, and they looked at their slope values. And what they found, so remember the hypothesis is that the smarter animals, humans, should have a smaller slope. But they found the opposite. Pigeons had quite a bit smaller slopes than humans. So if it's true that the smaller the slope, the smarter you are, well then pigeons should be smarter than humans. But they didn't come to a conclusion yet, because they said, well, wait a second, maybe this wasn't fair, because when we tested humans, they used a keyboard and a monitor. Pigeons, they had them peck at a screen. So the stimuli came up on like a touch screen, and they had to peck at it, because pigeons, I guess, don't have the dexterity to do it with their claws, fingers, toes. So they said, okay, well, maybe that's skewing the results. Let's retest humans and have them peck at a screen. So it's probably easier to have humans peck than it was to train pigeons to use their feet. So they did retested people pecking, and they looked at the slope value, and they found it was actually even higher. So this contradicts the hypothesis and suggests that there's no relationship between the slope of your Hick-Hyman equation and intelligence. Alternatively, it could be that pigeons are just waiting to take over the world. So watch out for pigeons. Now let's go back to our baseball example. So in this example, let's imagine we're comparing a pitching machine, so the same pitch every time, to this kind of simplified example where there are 6 different types of pitches. So how would reaction time change for a batter in simple reaction time, pitching machine, to a pitcher throwing 6 different pitches? Well, what we're going to need to know here is, well, in baseball, for a batter, what is the average slope and y-intercept? And I actually found a study where they measured reaction time somewhat artificially for the same pitch every time, 2 different pitches, or 3 different pitches. And I took these data, I plotted them in Excel, and I asked Excel to tell me the slope and the y-intercept. And we're going to use these to guess a batter's reaction time in simple reaction time versus 6-choice reaction time. So we'll need these values that came from this study. All right, so first of all, let's imagine just one pitch. So we're going to start with the equation of Hick's law, and we have one stimulus response alternative. So log to the base 2 equals 1. If we rewrite that as an exponent, that's 2 to the power of 0 equals 1. So remember, this is the case where it equals 0. So we're going to have 0 times m, that's going to disappear, and reaction time is simply equal to b, or the y-intercept from the equation. And from our last graph, we saw that that was 325. So if we throw the same pitch every time to a batter, the reaction time is going to be about 325 milliseconds. Okay, what about 6 pitches? So we're going to redo this equation, but now we need to put in 6. 6 is from this example, and that's kind of a weird log to solve, so I've asked a calculator to solve this logarithm. So we know log base 2 of 4 would be 2, and log base 2 of 8 would be 3, so it's got to be between 2 and 3, and my calculator said it was about 2.6. So reaction time is 2.6 times m plus b. We're going to use m and b from that previous study. So b was 325, the slope was 69.4. Calculate our answer here, we get reaction time is 505 milliseconds. So this is obviously why a pitcher throws many different pitches, because that will increase the reaction time or make it more difficult for the batter. And if you think of that slope value, so here the idea is that every time the pitcher doubles their number of pitches, reaction time will increase by about 70 milliseconds. And it's not hard to go from 1 pitch to 2 pitches. That will increase the batter's reaction time by 70. To increase it another 70, the pitcher has to go from 2 to 4 pitches. Not that hard. But then to keep it going up 70 every time, the pitcher has to keep doubling the number of pitches. So from 2 to 4, 4 to 8, 8 to 16, 16 to 32, and we're quickly getting into large numbers. Maybe it's hard for a pitcher to have 32 different pitches. They want to slow the batter down even more, they're going to have to go to 64, then 128, then 256, then 512. And we're probably getting into the limits of the number of different types of pitches and speeds and locations that a pitcher has. Okay, in our last part of this module, let's talk about exceptions to the Hick-Hyman Law. So we see the Hick-Hyman Law almost everywhere and almost all the time. So it could be a very simple keyboard task. It can be a batter against different number of stimulus response alternatives. But it could also be when you go to the grocery store and you want to buy cookies. And if you're looking for a type of cookie where there's just one type, you're going to have a very simple reaction time. I'm always surprised the number of alternatives for Oreos. I should count how many different choices you have in just Oreos, like just name brand Oreos. There's mint ones, There's thick ones, there's thin ones, there's double thick ones. It's surprising. I guess Oreos, they're doing very well for themselves. So if you want to pick Oreos and you don't know which ones you want, you're going to have a longer reaction time because there's so many more stimulus response alternatives. There are a few times, so even though Hick-Hyman Law works almost all the time, there's a few times where it doesn't work, where there's an exception. Now, they're not such big and common exceptions that we say, oh, no, the Hick-Hyman Law has been destroyed. No, it still works most of the time, but there are interesting exceptions that tell us more about the boundaries of this law of human behavior. We're going to look at two of them. There's a few other examples. We'll look at saccadic eye movements, and we'll look at extensive practice. For both of these, the reason we see an exception is that the choice has become automatic. And whenever the choice is automatic, or in other words, response selection is always the same, so 1 choice, short response selection, 10 choice, short response selection, you can imagine that is going to violate or be an exception to the Hick-Hyman Law. Okay, first up, saccadic eye movements. So in this experiment, the first thing we wanted to do was just replicate basic Hick-Hyman Law. So they set up an 8-choice task. You're using your 8 fingers in this example, and there are 8 stimuli, so just lights that turn on. And if this light illuminates, you should press the A key. If that one, it's S, and so on and so forth. So you tested 8-choice. Should have the longest reaction time there. 4-choice, a little bit easier. So now you're just using 4 fingers, 4 stimuli. 2-choice, and simple reaction time. So here are the results. And of course, they replicated the Hick-Hyman Law. We see that when we transform the data with log base 2, it looks linear, suggesting that there was a logarithmic relationship between reaction time and the number of stimulus response alternatives. So far, everything is good. We've replicated Hick-Hyman Law, no exceptions. And remember, why we're seeing this relationship is because as we increase the number of stimulus response alternatives, say from 1 bit to 2 bits, this would be 2-choice, this would be 4-choice, response selection increases, and that increases reaction time. So in that first experiment, remember the stimuli were kind of curved, and they did that to be similar to their second experiment. Here, instead of pressing a key, what they did is they had you looking at a fixation with 8 possible lights, and this is supposed to depict the participant's eyes. And what you're told to do is when a light illuminated, just look at that light. So light turns on and look at it. So move your eyes. And they measured the reaction time for your eyes to move or to jump from the fixation to the target. And that sort of eye movement is called a saccade. When your eye goes from one location to another, I try to do it without moving my head, that is a saccade. More specifically, we're going to call these prosaccades because you're looking towards the target location. So here's 8-choice, stimulus. One of the 8 lights turns on and you look at it. They, of course, tested 4-choice, just 4 lights, 2-choice, and even simple reaction time. So what did they find here? What they found was an exception to Hick-Hyman Law. So look how reaction time is the same, regardless of whether it's simple reaction time or 8-choice reaction time. Your reaction time is the same, and that's not supposed to happen. Reaction time should increase with the number of stimulus response alternatives. So here what's happening is response selection is always the same. 2 choices, short response selection. 4 choices, short response selection. It's always the same. Why does that happen? Well, the reason it happens is because different areas of the brain are involved in these different conditions. When you have to see a light and press a key with your fingers, you're going to use many areas of the cortex. A lot of areas would be involved to detect the visual information, to make a response selection, and then to program that movement. So a lot of the cortex is involved. And that's when we see Hick-Hyman Law. When a light turns on and you have to look at it, you don't need to use your cortex. It's a very simple, reflexive movement that is part or done by the oldest part of our brain, the brainstem, and specifically the superior colliculus. We're going to see this structure again when we talk more about vision. But if a light turns on and you want to look at it, the brainstem can do that for us almost outside of conscious awareness. And when we use the brainstem, it doesn't seem to care about the number of stimulus-response alternatives. There could be a light anywhere in the world. If a light suddenly turns on over there and I look at it, my superior colliculus, my brainstem will do that for me, and it doesn't care whether there was one light that could have come on or an array of thousands of lights around me. So the researchers here had an interesting hypothesis. They said, okay, well, is it that all eye movements are exception to the Hick-Hyman law? Or is it only eye movements that are controlled by the brainstem that are exceptions to Hick-Hyman law? So the way they tested this is a very simple change to the experiment. And we see this kind of over and over. We'll see it many times in the course in cognitive psychology research, that we do very simple changes to experiments that almost seem like they wouldn't make a difference, but theoretically, the difference is huge. And let me introduce this one. So what they told participants is, again, they tested them 8 choice, 4 choice, 2 choice, simple reaction time, eye movements again. But what they said, when the light turns on, instead of looking at it, which would be a prosacade, we want you to look in the opposite direction, which is called an anti-saccade. And this seems trivial, right? Okay, light turns on, look in the opposite direction. Sure, that's still quite an easy task. So here's 8 choice. If it was that light, you should look in the opposite direction, and so on and so forth. They also did test 4 choice, 2 choice, and simple reaction time. The interesting thing is prosacades, light turns on, look at it, that uses superior colliculus. Anti-saccades, they're complicated enough that the brainstem doesn't know what to do in that situation. The brainstem is a very simple, very fast structure. It can only handle the most reflexive, obvious sorts of behavior. Being very simple is what allows it to be very fast and automatic. Now, an anti-saccade doesn't sound very complicated, but it's too complicated for the brainstem. Light turns on, look in the opposite direction. The brainstem would say, I'm out, I can't do that, I don't know what you want. Ask the cortex, ask the higher evolved, more complex areas of the brain. So a prosacade, we could use the brainstem. Anti-saccades, it's still eye movements, but we're going to have to use basically the same areas of the cortex that we saw with key presses. So what happened in terms of their results? So here's key presses, Hick-Hyman law, prosacades, no Hick-Hyman law, and the interesting thing here is that with anti-saccades, we're back to seeing the Hick-Hyman law. There is an increase in reaction time with the number of stimulus-response alternatives. It doesn't have the same slope as manual key presses. It probably doesn't have the same y-intercept, but that's okay. We're still seeing an increase in reaction time with the stimulus-response alternatives. So we go back to the hypotheses. These results supported that it's only eye movements controlled by the brainstem that are exceptions to the Hick-Hyman law. So it's not that eye movements are magic, it's when eye movements are controlled by the brainstem. The brainstem doesn't seem to care about the number of stimulus-response alternatives, and that violates Hick-Hyman law. All right, let's look at another example. And here we're going to see that we can also violate the Hick-Hyman law when the cortex is involved. That we will violate the Hick-Hyman law if the brainstem is involved, but it can also occur with the cortex. And this is the case with extensive practice. Now there is a study that had a participant do the typical Hick-Hyman task for a whole semester. They had them come in several times a week. They did thousands of trials, and they looked at how their performance changed over time. That is a difficult study to do. There was one very motivated participant who wanted to do it, but it would be hard for me to convince all of you to come in 3 times a week and do this simple experiment over and over and over. So this researchers decided another way to do this experiment. They said, let's find something where we don't have to give people extensive practice, but they likely have had extensive practice by the time they're a young adult. And their idea for this was digit naming. So in their experiment, they would show you a digit and you would have to name it. So if a 1 comes up on the screen, the participant should say 1 as quickly as possible. And how much practice have we had doing this? A ton. It's hard to even guess how many times we've done this. Whenever we see a number, our brain now automatically thinks of what the name of that digit is, because we've practiced this so much. First, quite explicitly when we were children, we practiced this in school, but anytime we're doing math or numbers, this is constantly happening. So the argument is, by the time you're a young adult, you have had extensive practice digit naming. So what they did is they did various versions of stimuli. It could be 10 different stimuli, which, this is a little hard to solve the log, so it's 3.3. 8 choice, well, we know log base 2 of 8 is 3. So the ones in bold, these are the ones that are easier for us to solve. So they did this experiment. So for example, in 2 choice, the participant knew that it would either be 0 or 1. Those are the only 2 digits they would see. If it was 0, they would say 0. If it was 1, they would say 1. So here are their results. So at first, it might look like there's an increase in reaction time, but notice how zoomed in we are here on the y-axis. And when they looked at these reaction time values, they found that they were comparable. There were no significant differences. So here's 2 choice, here's 4 choice, here's 8 choice, and reaction time is the same, regardless of the number of stimulus response alternatives. This is a violation or an exception to the Hick-Hyman Law. And you might think, okay, well, maybe with extensive practice, they're using their brainstem. And if we put these participants into an fMRI scanner, had them do the task and see which part of their brain they were using, it wouldn't be the brainstem. This is too complicated for the brainstem. It would be the cortex. But what has happened over extensive practice is that selecting which digit to say from a list of alternatives has become automatic. Once we've done this enough, our brain no longer cares whether you're going to give me 4 different digits or 8 different digits. It has become automatic at seeing a digit and naming or thinking of the name of that digit. So it's not just when we use the brainstem that we see an exception to the Hick-Hyman Law. It can also be with extensive practice. Ooh, I had an idea when I saw this experiment. I said, okay, well, when would this become automatic? So this experiment was with young adults, say, 20-year-olds. But what if we tested 15-year-olds? Would they be automatic? Would we see an exception, like a flat line, or would we see Hick-Hyman Law? If they did, well, what about 10-year-olds? And I managed to find a study. They did this task in 1st and 3rd grade students. And what they actually found in 1st and 3rd grade is these students were already automatic at naming digits, which I was kind of surprised. I thought that young, you wouldn't have had extensive practice. So it looks like you'd have to test even younger students to find the Hick-Hyman Law relationship with digit naming. All right, we saw 2 exceptions. So with saccadic eye movements, remember the brainstem caused the exception. With extensive practice, it was the extensive practice that made the relationship automatic and caused the exception. And overall, the way we can explain both of these is whenever response selection is automatic, and by that I mean it's the same duration for 1 choice, 2 choice, 4 choice, 10 choice, we will see an exception. And there could be different reasons for that. It could be because you're using the brainstem, or it could be that you've had extensive practice with the task. All All right, last example here relating kind of Hick-Hyman Law to user experience design, or UX design. And we're going to delve more into this topic when we talk about compatibility. Now imagine you're using this universal remote, all sorts of buttons, versus a very simple, kind of maybe an Apple remote. Well, there are very few, over here we have very few buttons, very few choices, so you're going to have a shorter reaction time. And over here, there's so many choices, so you're going to have a much longer reaction time. That is fundamental to Hick-Hyman Law. I guess if you had extensive practice with this device, years and years of using it, you could become automatic at this task. But the idea is, well, maybe we want to use this device because our product will be easier for users, thus more appealing, and will sell more products. So that is something considered in user experience design. And this can be very important whenever safety is involved. So, using your television probably doesn't invoke safety issues, but you can imagine a nuclear power plant. If something goes wrong and you need to find the correct button out of hundreds or thousands of buttons, that's going to take a long time and could result in a catastrophe. And we're going to see examples of this in our next module when we talk about stimulus response compatibility, which is also very important to user experience design. That's the end of our second module. So good luck with the test, and I'll see you again soon.